let's talk about something that's a huge part of energy engineering these days: wind power. It's a technology that feels both ancient and super futuristic at the same time, and we're going to break down exactly how it works. So it all boils down to this really cool question, right? How do you take something you can't even see, the wind, and turn it into the very tangible power that lights up our homes and keeps our businesses running? That's the puzzle we're going to solve today. Okay, so first things first, what is wind, really? I mean, it's more than just a nice breeze. From an engineering standpoint, it's simply air that's moving. And anything that's moving has what we call kinetic energy, the energy of motion. And that energy is just sitting there waiting for us to grab it. So officially, wind energy is a two-part trick. First, we have to capture that kinetic energy, the wind's motion, and use it to create mechanical rotation, just like a little pinwheel spinning in your hand. Then, that spinning motion is used to drive a generator, which is what actually makes the electricity. It's a really elegant energy conversion when you think about it. Now this is one of the most crucial principles in all of wind power engineering. The amount of power available in the wind doesn't just go up a little as the wind gets faster. It goes up by the cube of the wind speed. So, get this. If you double the wind speed, you don't double the power. No, you increase the potential power by a factor of 8. It's wild. And that's exactly why finding the perfect windiest spot for a turbine is so incredibly important. Okay, so we know the wind is packed with a ton of potential energy, but can we grab all of it? Well, not so fast. This is where the laws of physics step in and say, hold on a minute. There are some very real limits to how much we can actually capture. And that hard limit, it actually has a name, the Betz limit. Way back in 1919, a German physicist named Albert Betz figured this out. He realized that if a turbine was somehow 100% efficient, it would literally stop the air dead in its tracks. But if the air stops, no more wind can flow through, and the turbine would stop spinning. So because of that paradox, he calculated the absolute maximum you could ever capture is just under 60%. And this really shows you the difference between a perfect world on paper and the real world, right? While 59.3% is the absolute best that physics will allow, our modern turbines, with real-world stuff like friction and other losses, usually operate somewhere in the 35 to 45% efficiency range, which, by the way, is still a massive engineering win. So if we can't just use the theoretical maximum, how do we know how a specific turbine is actually doing out in the field? For that, engineers use something that's basically its unique operational fingerprint, the power curve. It's one of the most important tools in the entire industry. And this is it. This is the power curve. It might look a little technical, but it tells you everything you need to know. Along the bottom, you've got wind speed, and going up the side, that's how much electric power it's putting out. Understanding this chart is absolutely key to figuring out how much energy a wind farm can produce, and for keeping an eye on its health. You can pretty much see the whole story of a turbine's operation in 3 main stages right on this curve. First up, you've got the cut-in speed. That's when there's just enough wind for the blades to start spinning and making a little bit of power. Then, as the wind picks up, the power climbs until it hits the rated speed. That's the sweet spot where the turbine is cranking out its maximum, most efficient power. But if the winds get too crazy, we hit the cutout speed, where the turbine hits the brakes to protect itself from getting damaged. But here's the catch, and it's a big one. That power curve we just looked at, that's the fresh-out-of-the-box, perfect conditions version. As this quote points out, in the real world, no 2 turbines are exactly the same, not even 2 identical models sitting right next to each other on the same hill. And that real-world messiness brings us right to the practical trade-offs of wind energy. Just like any technology, it's not a silver bullet. It has some really clear advantages, but also some significant limitations that engineers have to work with. On the one hand, you've got some amazing benefits. The wind is clean, it's never going to run out, and you don't have to pay for fuel. But, and there's always a but, you've got some serious challenges too. The wind doesn't always blow, the upfront cost to build these things is huge, and there are real local concerns about things like noise and the impact on wildlife. It's a constant balancing act. So, all of this leads us to the big challenge for wind engineers today. How do you close that gap between the perfect theory on a spreadsheet and what's actually happening out in a windy, unpredictable field? This is where data really becomes the hero. See, that power curve isn't just a static chart you look at once. It's a live health monitor. It's like a heartbeat for the turbine. By constantly comparing a turbine's real output to what the curve says it should be doing, Engineers can spot tiny problems. Maybe a blade is slightly off angle, or a gearbox is starting to wear down, long before they turn into a catastrophic failure. And this is where things get really clever. Instead of comparing a turbine to some generic spec sheet from the factory, what if you compared it to all its buddies right next to it? In this chart, the orange line is the average performance of all the turbines on the site, and the blue dots show what one specific turbine, T14, is doing. This is a much better way to see if a turbine is truly underperforming, because it automatically accounts for the local weather everyone is experiencing. So what's actually causing a turbine to fall behind? Well, it's a whole bunch of stuff that happens out in the real world. The density of the air changes with the weather. The wind isn't a smooth, perfect flow, it's turbulent. Blades get caked with dirt or ice. And over time, parts just get old or knocked out of alignment. Every single one of these things can eat away at a turbine's efficiency. So, we'll leave it with this, a challenge really for any of you who are aspiring engineers. We've got the theory down, from kinetic energy to the Betz limit. We can see the messy reality of it all in the power curve. The big question for the next generation is this: how can we use the mountains of data these machines produce every single day to better diagnose, predict, and ultimately close that gap between what a turbine could be doing and what it's actually doing in the field?